we'll meet next Thursday as well, and then I think I'll read you one other one, but pretty much we're gonna be right on schedule. So hopefully we can finish up most of this today, and then we can start rotating black holes tomorrow, or certainly by Monday. I'm looking for that one derivation that I told you about that I photocopied at some point. I know I scanned it, but I cannot find the scan at all. And prefer not. I don't even know I already have the derivation anymore. When I moved offices, I got rid of a lot of stuff. And I think I got rid of the journal that actually had the derivation in it. So I don't think I can remember who did it either. So I'm hoping I have it someplace. But I'm not going to go over the derivation of the rotating black hole because it's idiotically long. It's just, and that hurts. So we're just going to start with the metric. Okay. So that said, let's kind of review what we did last time. So we have our metric here like this. And we're finally using natural units. Okay, because frankly, that polarity dropping factors of C. This is, I think, why everyone goes to natural units, because you get polarity dropping factors of C. So you go to natural units. Okay, so we have this right here. And the problem with this is with these coordinates here, we cannot see inside the black hole that easily. And so we realized that if we switch from T to R to basically V to R, this one here, this allowed us to go inside R less than RS. So we're inside actually the event horizon. That allowed us to do that. The problem with this is that we saw, it's not a problem with this, is that there is right here that there's a symmetry between T and minus T. So in this case here, this V here, we're going for, with the V here, this is going forward in time with T increasing. Well, if you have a radial line going into the black hole with T increasing, then the corresponding radial line going in with T with a minus T should also exist. And we saw that we could do that effect if we actually use V. So in that case, we can accomplish this. We could get the radial light ray going into black hole. If we used go into the black hole for T going to minus T, in other words, going backwards, if we used R, the U, and R, that works. Well, we still want to be able to go into the black hole in forward in time. So what we're going to do is that we're going to switch to U and V. So we switch. So to account for both the radial, the radial inward light ray, or plus and minus T, we will rewrite our ds squared in terms of U and V. And that was daily homework. What was that? All my daily homeworks and everything. You're going to do that one in daily homework 12. Okay. Which is technically due today, but frankly, if you get into me later, meeting in the next week, I'm okay with that. Because I'm just a little behind in Brady. So I'm okay with that. That makes sense? So what did that give us? That's gonna, what you're gonna prove is that this is gonna give us this thing. That gives us that. Now, the problem is if you remember what the V's and the U's are. Remember our, when we had this T plus R star equals V. And this T plus R star equal minus R star equals U. The problem is that as R goes to RS, and what we found out is that this R star goes to minus infinity. So V goes to minus infinity, and U goes to positive infinity when R goes to RS. And we wanted something more fun. We wanted basically the event horizon to be someplace close. And so we realized, well, if this R star is going off to minus infinity, if I were to take the exponential of that, well, e to the minus infinity is 0. That's going to be something finite. So that suggests that maybe the coordinates we ultimately want to go to basically pull these points into someplace realistic or someplace that's not infinity, is we want to look at the exponentials. So that was going to be basically the whole idea behind the. I'm going to look at the whole of 10. The Kuskal coordinates. So what we're going to do here is that to bring V and U to a finite value, we will transform to the new coordinates, to the new variables. Okay. V prime and U prime. So this one here, we're going to say V prime is going to be this E. We're going to take V and we're going to divide it by 2 R sub S. This is just to make it dimensionless here. And then we're going to say U prime is going to equal, we're going to put a minus sign there. And I think that minus sign must be by convention. I wouldn't have put it there, but Kuskal or whoever did this first put it there. So it's stuck. This is going to be here. And if you look here, the version I gave you here, I was using the version that Carol was using instead of, so he has a 4GM, and the 4GM is really just 2 arms. So that's just like that, again, in natural units like that. Does that make sense? So in this case here, this is when R goes to R star, our V goes to minus infinity. So V prime goes to 0. And this one here is when R goes to R star, U goes to positive infinity. So U prime will then go to 0. This is not minus 0. So that's the first stage. Then what we do is we then go to the final Kuskal coordinates, and that's going to be in terms of this capital T, which is by definition 1/2 V prime. A little better. I think he has V going first, doesn't he? Yeah, he has V going first, and then this R. V this. Okay. So these right here, these are the Kuskal. Okay. So we actually work these out. And what did we find out happens? Let's just kind of, we'll do one of them again, then we'll just jump to the other. Did we do T? We did T last time, right? So why don't we just do this thing? So let's just, all right, so this is gonna be 1/2. All right, V prime is my buddy here. V prime is gonna be this e to the V over to the S. And this is gonna be minus and a minus, so plus e to the minus u over to our S. And then what is our V? Our V is T plus R star, and our R star is R plus RS. Ln of R over RS minus 1. Over the two S. And this one is in plus e to the minus T minus R plus RS ln I over RS minus 1 here, here. Okay, so we said what comes out here? Well, if you look here, you can see that I can have a little r over 2RS, a little r, ooh, over 2RS seconds. That, and then everything will have, then we're gonna have this guy here, e to the, and also then the other factor comes up as well. The other r part here as well, so I'll put that in. E to the, they cancel here, 1/2. I'm sorry. 1/2 ln R over RS. One that part also comes out, then you're left with the e to the t. This is e to the t. Now, what does this piece here go to?
Hyperbolic sign. Cosine.
Cosine, because it's an even function. Okay, so this is some cosh, right? This is going to be that's Cauchy. And then the other one we had the section. And then what did we say happens with this guy here? The 1/2 goes up here, making the 1/2 power. Then we exponentiate the logarithm. So that gives us this square root of R over RS minus 1 times this e to the R over 2RS times the cosh t. That's what that capital R is. Makes sense? And then yesterday we showed that this t equals the same thing. With the search. Okay. That good? Now, let's make a graph of some space here. And I'm still clear. I still am. Okay, let's start making a graph. So let's actually now graph this TR. Let's see what we're still getting. So first of all, what do you notice here? Let's say if we look at what would be R squared? Let's look at T squared minus R squared. Is that the way he does it? Yeah, he's gonna do that one. Okay. What would that equal? Let's work it out. So I get this guy here squared. This guy squared. They cancel. You got my cosh square root of t. And minus the same thing here. What do you notice about that? Factor out this guy. And then we'll do this. Still fitting. What do you notice about that? Particular, this guy right here.
Well. You make,
No. It equals something. What's it equal? I think maybe it did equal 14.
well, 1 minus,
It equals 1.
no. I thought it was plus.
It's minus. Hyperbolic sign comes with the minus.
Oh,
Daily homework 14. I'll write it up. I'll hand it out next time. That equals 1. So then what does this thing equal here? This t squared minus r squared equals here. Just something that depends on r. Okay, right. So this is going to be a constant for fixed r. In particular, what kind of constant? I mean, okay, so it's going to be, if the little r is fixed, what is that the equation of?
circle. Or something along those lines.
This is what happens when high school tries to rush through the calculus. All this beautiful stuff has been lost. I think I was the last generation trained. Okay, I think I was the last generation trained with any level of depth of analytic geometry. That's our buddy. Let's. Okay. If I were James Bond, no, I'd be petting my white fluffy cow. Okay, no, say the circle. I'd be walking out the door and pressing a button and the walls would start coming in, and I'd be petting my white fluffy cow saying, so it is an ellipse, so which is a circle. And so you both realize it's hyperbole. Okay, so they're gonna be the conditions for a hyperbole. So what would that look like? So what would it look like? So let's say we have R let's say R is greater than Rs. What would that mean? So if R is greater than Rs, this constant here is positive. Okay. So we're basically going to have t squared minus r squared equals basically a positive constant. I just say positive constant. Okay, so do these go like this, or do these go like this, and convince me? Okay, well, let's solve for t here. I just call when this is positive. Okay. Can your t ever equal 0? Can never equal 0. So which way does it have to be? Is it this one? These ones. Has to be this guy here. Does that make sense? So this would have to be something that goes like this. And this would be for constant r. Did he plot which would it be? These? Okay, just something I'm going to be different. So everything's right there. It's just something's okay. I had lunch with my daughter and I got a beer. I should not have had her for breakfast. I'm a little scattered right now. So is that this here?
Oh, is it because
It goes the other way.
for t minus r, you have cosh minus sine t or sinh?
No, these are all.
Oh,
What do you mean?
like for you have
Oh, you're saying up here.
Yeah.
Oh, okay, that's. I had these flipped. Is what you're saying.
Yeah.
Okay, so this should be the cinch. Yes. Gosh. So this has to have a minus sign up there. Okay. So if that's a minus sign up there, everyone's here. I apologize for that. So this is going to be a negative constant. So this is going to be the t squared equals r squared minus c. Okay. Now, can your t ever be 0?
yes.
Yes, it can be. And so these are going to go the other way. Now I'm happy. This is going to go like this. And what will they represent? They will represent a line of constant r. Little r. So this is going to be a constant little r here. And this is going to be for the r greater than this. Now, what happens if r equals r sub s?
You get 0.
You get 0. That then gives you the t squared minus r squared equals 0. In other words, t equals plus or minus r. What would they be? They just be nothing but straight lines. So you can get lines that go like this. Okay. So these lines here are the r equals r sub s lines. They can asymptotes like that. They can look kind of prettier like this, prettier like this, prettier like this here. Okay, that makes sense. And so what I can do is I can have a whole bunch of different r values out here. This whole bunch of r ones like this, and these all represent different r's. These are all different arguments. As R gets bigger, which one would be a bigger R than this? If I were to say rank these, this is little R1, little R2, little R3. Which one would be the biggest one?
The bigger one would be further away from.
Exactly. Because this constant is going to become bigger and bigger and bigger. And so that means that actually this R here is going to be bigger and bigger. So this one here, these R's here, they get bigger this way like that. That makes sense. Bigger this way like this. And this right here, then these would be the shorter radius. Okay. Now what happens if R is less than 1? What do we have?
Then you have
Then you have the other one here. So in this case here, you're gonna get this guy fellow here like this. And so I'm going to put this these in black. So this is going to be ones that look like this. These are hyperbolas like this, and these are going to be for the ones that are nothing pursuits. What happens if little r is 0? Little r is 0. And this goes to 1. This goes to 0 minus, make a plus sign here. You're going to get ultimately what there's going to be is there's going to be some smallest one here. This line here. This would be r equals 0 here. And then there's going to be 1 here. This would be r equals 0 here. You can't get any smaller than that. Okay. So look at this is actually pretty cool. What happens? Our event horizon shows up perfectly here. We can actually see the singularity here. Now the singularity, what does it become? It's no longer a point, it becomes a spark here like that, but that's no longer. That's fine. Okay, that looks pretty good. Oh, what about the light cones for this? So when you actually go through and work this out, you're going to show get the following. Actually, let's do one more thing. What happens if I take the ratio of T and R?
That's hyperbolic tan.
Yeah, your these R factors come out here. And so you're just going to get the sinh T, the Rakasha T, which is just this here. Okay. So for a fixed T, what do I have? What would a mathematician call that?
Great.
Line. It's a straight line, yes. Okay, right? And what does the hyperbolic tangent look like? I'm going to say graph the hyperbolic tangent. Let's see, I'll look something that looks like, looks like this. So what are these going to be? These are just going to be straight lines in the side. So what's going to happen? I'm going to have lines like this. These right here, these are basically the lines. These are lines of constant T. That's what straight lines are in here. And this would be a positive T. Like this. This would be a T is positive. And one like this, I'll make it a dotted line. Okay. This would be line constant negative T. Where would be plus infinity and minus infinity?
Like R equals plus infinity.
No, T. Yeah, little t. If little t is minus infinity or little t is positive infinity, where are they in the sign there? What does a hyperbolic tangent do for infinite infinity? Negative infinity or positive infinity?
Is it plus or minus one?
It goes to plus or minus 12, right? Because this is 1. And this is your minus 1. Okay, that makes sense. So where would they be here? This line here is also corresponding to basically t going to minus infinity. And this line here is corresponding to t going to positive. That makes sense. Again, this line right here, the straight line here, this is your R equivalence here. But it turns out this is the transformation that keeps giving. Okay, let's see the metric in your homework. You're going to actually work this out. And then the following. So you do a shell. And then daily homework 15. That's your ds squared. And then 32g squared m cubed over little r. E to the minus r over rs. Minus dt squared plus dr squared plus little r squared dr. Am I off the edge there? I am not. So notice that singularity that was occurring at r equals rs, that's no longer there. The only true singularity you have in this problem is where? In the short-shelled metric, where's the only true singularity? Before there was that one that looked like we're getting, remember when you're at the short-shelled radius, the G00 component, the G11 component was going to inflate. That's a fixed singularity. Here, you're actually seeing the only true singularity we have. Where's the only true singularity we have in the short-shelled metric? When little r is 0. That's the only true singularity you have in this here. The other problem was basically just the coordinates were weird. And this you can see it's showing it quite well. But tell me how the light cones look here. The light cones are really, really nice here. What are the light cones in this case? What do they look like? You're pros at light cones. And again, we're looking at the radial light cones. So for radial light cones, what do?
S squared and d omega squared 0.
Okay. So what are you left with?
dt times all of that.
Minus dt squared plus dr squared has to equal 0. So your dt over dr squared equals 1. So your dt dr is plus or minus 1. So what do these look like no matter where you're at? The straight 45-degree ones that we had before. That looks beautiful. So the light cone here is this. The light cone here is this. Actually, let's make I want to make them look similar. This is going to be this guy. Light cone here is this guy. So if you're here, how's the light cone look? It's like this. Okay. What happens if you go into the black hole here? Will that light ray ever come out? If I'm here, how's that light ray still have to look? Like that. Will that ever come out? No, you can see this is going to go parallel to this line here. Okay. That makes sense. So So again, what we're trying to do, we're trying to find out all the coordinates that basically that this metric allowed us to have. And in the process here, we ended up with actually a little bit more physics. If I were to say, where do we live in this world here? In this world right here, where is us? Well, that's a really busy graph. So let me kind of simplify this. So what do we have? These are already S, S. Then we have the slide goes over here. And this slide goes over here. Where do we live here? R greater than R. Okay. So this is us.
Yeah.
We are here. Okay. And this is the region of thought space. Well, what are we getting in this case here? So he calls this region 1. I think he calls it region. Yeah, he calls that region 1. Where would our black hole be?
R equals RS.
Here. So if we're sending a light, if we're here, if I'm sending a radio light ray into the black hole, it's this. This is a radio. That's a radio light ray going into the black hole. Okay. So this is our region here. So we're going to call this region 2. So this is kind of our black hole. Okay. Now, this predicts to the regions here. Okay. We get this region here. Okay, so this is our black hole here. What is this region here?
Also black hole.
No, let's see. If I have light right here. Are we getting out of it? Sure are. Not just that. Did you ever stay in this region? You can't stay in this region. But if you're in this region, eventually you have to come out. You can't stay. Okay, so that's not going to be a black hole. It's going to be a white hole. So this is right here. This is the white hole. And it's basically a time reverse. Left. Okay, what did we do? We assumed that we had that symmetry, that minus T symmetry. And that's the consequence of that, is that we get a white hole. He calls that region, he calls this region 3. But now we get something new. What else do we get? We get this region out here, and if we go out far enough, we're going to get flat space. So we get a brand new universe over here. But basically, I have a flat space here. So this is a whole new universe here. This is a new region of space. It's basically a new universe. He calls this region 4. Now, can we ever communicate with the people here? So this is basically a new universe. Can we communicate with them? In order to communicate with them, what do we have to do? We have to send a light ray. Can we send a light ray? We live here. Is any light ray going to get to the region? We can never communicate with those people. Okay. So they can all be happy here and doing just one of the things over here. And guess what? We can't communicate. Okay. That's kind of neat. That's a whole brand new region.
Why can't you communicate?
Okay, so here's a light ray. So we're going to send out. We're going to go way in the past and send a signal like this. Okay, we're going to get there. It has to go here. That light ray can't go like that.
It has to go parallel.
They can only go this way. That's all the light rays can do. Well, no matter what, because they're light cone. With this, it's always fixed. We can never communicate. Okay. Now, there is one way we could do that. Is what would happen. This person here could say, I'm done with life. This person here could say, I'm done with life. Okay. We're gonna jump into the black hole here. At the same time that we jump into the black hole here. And then basically we can kind of share building together for one brief. So I don't recommend it. Not just that, if you do, can't tell anyone about it. You could have a wonderful discovery. Hey, there really are people over there. And what's that? You can't send the light signal back. You can't have enough time to chat with the person who didn't find out all the fun stuff. That makes sense? Now we get more here. This is the problem that keeps getting, okay? This one's harder to. We'll reserve the first one. Okay. We got one more thing, and that's gonna be the wormhole. But it's a weird wormhole that doesn't always help you. Okay. So I think if I were Kuskal and came up with those coordinates, and I had this, I'd be going around the entire neighborhood telling people what I've done, whether they cared or not. I think this is probably one of the most amazing transformations I've ever seen on anything. That diagram it's called a Kuskal diagram. It's utterly amazing. Okay. There is, just so you know, I always learn Kuskal. There is periodically you'll see, and he has it in there. Okay, so if you turn to his page 215, he says that periodically it's called Kuskal. So I'm not certain how you pronounce that last. Do you know the name? There's so the Chris. So sometimes you'll see this. I don't know what those they got. Pardon me, this. So sometimes you'll see Kuskal, and I honestly don't know how to pronounce this. Zekris coordinates. So sometimes you'll see that. Okay, if that happens, again, when I went through, it was only for Kuskal. This guy gets attached. What does that mean? Most likely means that this guy did work actually probably independent of Kuskal, and no one really realized it, and they felt bad that basically my gut feeling would be. They felt bad that this guy did the work at the same time as this fellow didn't really get the right recognition. And so this is just the way of saying that I did equivalent work. Probably what happened, although I don't know. I feel like I don't know that. This is cool. Not the most obvious thing, but once you get it, it's fairly helpful. Okay. We do the wormhole tomorrow, then I think we can actually start doing rotating black holes.